Hi everyone. Um, I'm Takahiro Nozaki. Today, I'd like to talk about my research entitled Human Enhanced Future Society Opened Up by Advanced Robotics. And also, I'd like to introduce the research of my laboratory today. Mhm. First of all, let me introduce myself. I'm an assistant professor at Keio University, Japan. And my expertise is power electronics, control engineering, and robotics. For more information, please visit our website. This is a link of my laboratory. And if you have any problems or need help while you are in Japan, please feel free to contact me. Let me explain more about my research field. My research field is related to power electronics, motion control, motor drive, haptics, or robotics. In If we think about robotics, some of the researchers field between computer vision or computer processing and the robotics. But I'm studying on the power side or physical side rather than that kind of computer system. Okay, then let me start about talking about the main topic. Humans using five senses to perceive this real world. And if we think about motion, three sensations are very important. Uh, Three out of five sensations. Those are auditory sense, visual sense, and haptic sense. And we humans have already developed a lot of devices using auditory information or auditory technology and visual technology. And those devices are already used as practical use. So I believe haptic technology will be the sensory technology of next generation. Let me explain the difference between the haptic sensation and the other two. I mean, the auditory sensations and the visual sensations. The latter two sensations are passive. I mean, uh, even if we use auditory technology or visual technology, it's impossible to change the world. But if we use the haptic technology, we can touch with something or we can manipulate something. That's mean the tactile or haptic sensations are active sensation. And this technology is capable of changing the situation or this real world by physical way. Uh, But if we talk about haptic technology, we have to be careful because there are two different technologies. One is skin sensation. In skin sensation technology, we usually use vibration. I think most of you have your own smartphone and you have an experience to feel the vibration. This is the skin sensation. But the applications are limited to games or notifications. In contrast to that, there's another sensation technology that is tactile sensation technology. In this field, we usually use force, and this uh, technology is very important to design or to generate desired physical interaction. So today, I'd like to talk about this tactile sensation. Okay, and before diving into the detail, we have to think more about why do we need robots, or we have to think more about importance of studying robotics. Now, Japan is facing against a serious problem of aging society with falling birth rate. This is caused by three phenomena mainly. One is decline in young labor force. Second is increased burden of care. And third one is loss of skillful techniques. So we have to create an artificial workforce, and robots are the most promising solution for now. But the current robots have a serious problem. Actually, the conventional or current robots are developed from a position control system for cutting processes. The motorized system is used to make a desired shape. So this system should be stiff because when the tip of the drill makes a contact with the target object, and if the motion is fluctuated, then it's impossible to create a desired material. So in conventional world or in conventional robotics, the system should be stiff, and that was a performance index. But this kind of position control system has a drawback of low adaptability. If the target object is smaller than we thought, then the robotic system cannot grasp the target object. And if the target object is bigger than what we thought, then the target object may be broken or damaged. So position control alone is not enough to replace human work. Here you can see several motorized artifacts, but if we make a contact with these artifacts, there's a possibility of being injured. So we can say that these things are danger. Actually, there is an unrecognized shortcomings of existing motorized artifacts, and that is lack of tactile sensation. Here, this is the robotic hand we developed, and by using the tactile sensation, the robotic hand can grasp the target object. Here, the target object is blueberry or strawberry. But by using tactile sensation, we can, or the robotic system can notice when the tip of the finger makes a contact with the target fruit. And also by using tactile sensation, we can adjust how much force is applied to the target object. And in this movie, we used real haptics, and which is our technology. Here, there are two devices. If you move this system, then this system will track the position of this device. And when this device makes a contact with the target object, the operator can feel how much force is applied to the object or how stiff the target object is. So I mean, if this system contacts with like sponge, then we can feel the softness. And if this device contacts with aluminum block, then you will feel impact force and stiff feeling. This technology is called as real haptics, and this technology was developed by Professor Onishi, who is my supervisor. And next, I'd like to talk about essence of movement or motion. If we think about motions, we have to be careful about the stiffness. Stiffness can be represented by this equation. The stiffness K is a derivative or differential of force by position. If the stiffness is in a position control system, which is conventional technology, the stiffness is almost infinite. And actually, there's one another technology that is called as force control. In a force control system, the stiffness is almost zero. But as you can see in this, how can I say, this relationship, there's a duality between position and force. I mean, if you want to control the position, the stiffness has to be high. But if you want to control the force, the stiffness has to be low. So it's impossible to control both the position and force. That's the duality. And the characteristics of the position control system is like this. As I mentioned before, the position control system has characteristics of high stiffness, but low adaptability. In contrast to that, in the force control system, the stiffness is very low, and that kind of system has high adaptability. So force control is very important in contact motion. Next, I'd like to talk about technical difficulty of tactile transmission. This is the picture showing the physical interaction between human and the object. When we want to divide this physical phenomena into two systems, we have to achieve two things. One is position tracking. That means if you move this device, another device have to track the position of the operated system. This is the position tracking. The other is force transmission. If this device makes a contact with the object and applies some force to the object, then that force has to be transmitted to the operator side. These two controls have to be achieved at the same time to realize haptic transmission or tactile transmission. But as I explained you, to realize the force transmission, the system should be soft. And if you want to realize the position tracking, we have to control the position and the system have to be stiff. So there will be a contradiction between these two control goals. To solve this problem, our research group or my past supervisor, Professor Onishi, have developed a new approach that is called as acceleration-based bilateral control, ABC. Let me explain about the detail of the mechanism. As all you know, when the current flows, the motor will turn or rotate. Then we can express that angle as theta. And when a motor touches an object, it becomes difficult to rotate. In this case, some force is applied to the object. So now let's express the torque as tau. And in an acceleration-based bilateral control system, by differentiating the angle information twice, we can get acceleration information. And by dividing the torque by inertial information or mass information, we can get acceleration information. These two physical parameters are quite different, but by doing this kind of mathematical processing, we can get acceleration information from both physical variables. So by doing this deformation, we can control both position and force. That's the secret of the acceleration-based bilateral control. By using the haptic transmission, of course, we can transmit the motion from the operator side to the remote side. But our concept is not limited to that kind of teleoperation system. By using this kind of teleoperation system, we can record the human motions. And once we record the human motions, we can edit the motion data arbitrarily, because the recorded data is just the chronological numbers. So we can make the motion faster or slower than the original one, or we can scaling up or down the motions. And after modifying the recorded data, we can reproduce the human motion by using robotics system. That's a concept. Let me explain some examples. This is a dual arm teleoperation system using the real haptics. This is the experimental movie. The operator can watch the image. The image the operator is watching is exactly same as the image the robot is watching. And also the sound information is transmitted from the robot side to the operator side. And now the operator is feeling the stiffness of my hand and the force of handshake. This is balloon. Now the robot grasps the balloon, and the stiffness is transmitted from the robotic side to the operator side. And here you can see some space. That means the operator can feel the stiffness of the balloon. And please look at here. Here you can see plastic cups. This robotic system can grasp the plastic cups at the same time, and also adjust the force and grasp only one plastic cup. This system can perform this kind of handling motion, and also this system can grasp the fragile plastic cup with the soft motion, and also this robot can keep grasping while force is absorbed into the cup. By using computational approach, it's very difficult to realize, but by using human experiences, this kind of system can be developed. And we have established a startup company called Motion Leap. And Motion Leap have succeeded to implement this real haptics technology to the commercialized manipulator. Okay, so so far I explained about real haptics and the importance of haptic technology. And from now on, I'd like to talk about the potential of real haptics. By using real haptics, we can release humans from physical constraints. From now on, I'd like to talk about 4 constraints. First one is physical constraints. This is the example of prosthetic hand with haptics. This woman doesn't have her own right arm, but uh, this is robotic prosthetic hand we developed, and she can control this robotic hand by using this white device implemented to the big thumb of the foot. This is the experimental movie. This is the conventional robotic hand. She can control, or she can make the hand open and close, but she cannot adjust the force. But by using our robotic hand, she succeeded to grasp the fragile potato chips without any trainings. She can feel how much force is applied to the object by using this device. And we confirmed that she has almost same ability as the people who have their own right hand. And as I told you, we can edit the motion arbitrarily. If we scaling up the motion, original motion, that can be that will be useful for civil engineering or disaster relief. If we scaling down the original motion, that can be useful. That will be useful for medical care or cell manipulation. This is the example of the application of real haptics, and the real haptics is implemented to the excavator, which is the heavy equipment for civil engineering. This operator can feel how much force is applied to the target object, and by using this system, the operator can grasp the fragile or soft material. And also we have succeeded to implement the system into the actual cockpit or operational unit. And this is the scaling example of scaling down. This is a small, very small creature, and you can see the eye of the creature here and the arm of the creature here. We cannot manipulate the small creature without using this real haptics, but by using this system, we can feel the motion of the small creature. That's the example of edit of human motion. Next, let me talk about brain constraints. This is the damaged orange, and we have to pick up these kind of oranges before setting the oranges. And originally, human workers try to pick up this kind of damaged orange, but as you know, there's a limitation of the ability of brain, so they cannot pick up all of the damaged oranges. This is the robotic hand we developed. In this system, we recorded the worker's grasping force, and by combining this robotic hand system with the visual system, we can recognize the orange's condition, like size, the taste, and damage, then we can categorize the orange's property into several classes and select which data we have to reproduce. Then we succeeded to automate the fruit sorting process. And also we implemented the real haptic technology to the fruits packing system. This is another example. We implemented the real haptics to the rotary motor here, and the rotary motor is mixing the liquid. And by watching the relationship between velocity and the torque, we can estimate the viscosity of the liquid. This is not the example of teleoperation system, but we can implement the real haptic technology to this kind of motorized system. And the next one is space constraints. This is Singapore, and our university is here. He is a researcher in Singapore, and this drill is in our university. I mean, this is in Japan. Of course, there's a long distance between Singapore and Japan, but the researcher can feel the reaction of the drill across the long distance between Japan and Singapore. And this is another example. The operator is fishing, and he is in Tokyo, and the fish is in Oita Prefecture. The distance between Tokyo and Oita Prefecture is about 1,000 kilometers. He is in Tokyo, and the fish is in Oita Prefecture. But he can feel the reactive force of the fish, and they can enjoy the fishing. This is an example of solving spatial constraints. And this is another example. He is an expert of making a wall. And this by using this device, he can feel the reaction force of the wall and succeeded to make a flat wall. So this is an example of using 5G communication. 5G means the 5th generation. Most of we are using 4th-generation communication, but now we tangent from 4th-generation to the 5th-generation. And this is the proof of concept of using 5G communication. And we confirmed the ability or the good collaboration between 5G communication with the real haptics. By using 5G communication, we can reduce the communication delay, and we can feel more precise or vivid tactile sensations. The last one is time constraints. Here you can see operator here and the robotic arm here. And also we implemented real haptics to these systems. Now you can see two videos here. This one, in this situation, an operator is standing next to the robotic arm, and the operator is feeling the force. And we recorded the motion data. And in this situation, we sent the motion data to the robotic arm, and the robotic arm reproduced the human motion. And as you can see in this video, this robotic arm succeeded to grasp the bread, or open the toaster, or handling the bottle or glass. And the grasping force can be recorded like this. These are the angle information of the finger, and the velocity information of the finger, and the torque information of the finger. Now, there's a hot research field that is called as Internet of Things. In the field of Internet of Things, the researchers are trying to implement small sensors to all of the devices, and try to acquire a lot of data from the devices. But the IoT can be used for just sensing. But by using this real haptics technology, we can support the like all the people or patient by a physical way. So I think the next generation of IoT can be achieved by using this real haptics technology. This is another example. This is operator's finger, and this is robotic finger. Now we recorded the screw release motion. And now the speed is faster than the original one. So that means we can create work force, and we can increase the velocity of the motion. And the very important point of this movie is that we recorded only the motion for the hexagonal nut, but the motion can be applied to the square or tangential object, or triangular object, or this small hexagonal nut. By using the tactile sensation, the robot can get adaptability. This is the result of the conventional system. Without using the haptic technology, the system cannot adapt to the smaller nut. And also we can playback the motion. The original data is extracted from the screw releasing task, but by using the playback motion, we can release, or we can achieve screw tightening task. And this is the latest result. This is dual arm system. This is similar to the previous one, but the newest one. And by recording the data, we can reproduce this kind of handling operation. So by using this technology, we can enhance the areas in which humans can work. So far, we can manipulate the target object, which is in front of you right now. But by using teleoperation system, we can manipulate something across the distance. So that means we can solve the spatial constraints. And by recording and reproducing the original motion, we can use motion data in the future. So it will be possible to utilize your own motions at any place and any time by using this tactile technology. The total system is like this. This is the same picture I explained before. And, but we call this concept as Internet of Actions. The whole system is similar to the YouTube. We can download uh, a lot of various music or various movie from the YouTube, but we cannot download motion data from YouTube. But by using this concept of Internet of Actions, we can download uh, various motions and reproduce the motion. That's a concept. And finally, let me summarize this presentation. Real haptics is a high precision tactile sense technology. And this technology can transmit, record, and reproduce human motions. And as you can see from the prosthetic hand example, uh, by using haptic transplantation or skill integration or scaling up and down, we can release humans from physical constraints. And by using high-speed computational processing, we can release humans from brain constraints. And by using remote control or information communication like 5G, we can release humans from spatial constraints. And by using motion reproduction or speeding up or playback system, we can release humans from time constraints. Now, our research group are trying to promoting social implementation of this technology, and we have joint research with about 70 companies, and we have established Motion Leaf Inc. So these are the summary of this presentation. Thank you for your kind attention, and I sincerely hope that this program, JEMARO, will be a success. I look forward to working with you all. That's all. Thank you so much.
Thank you very much, Professor Nozaki. So that was a really great presentation. So I think we have a round of questions. So please feel free to ask.
Can I ask a question?
Yes, go on.
Nozaki sensei, konnichiwa. Watashi wa JEMARO no Ebru desu.
Oh, wow, what a
thank
good
you
Japanese.
for the presentation. It was like every page of it was full of interesting projects. And if I was not into flying and control so much, you were my #1 decision to study haptics with, but I want to work with you later on. So I have a couple of questions, if it is okay. On the 25th page of your presentation, there was a lady controlling the prosthetic arm with her thumbnail. And I think both actuation and sensing takes place in her foot, right?
Yes. The feeling is transmitted from the prosthetic to the big toe.
Oh, and do you think it is possible in the future to integrate that those electric signals into the nerve ends at her arm, her lost arm, so that her brain maybe like start to feel there is sensing there, maybe feel like it's natural again?
Yeah, I believe that's possible, but brain can send the command to the body. But it's a little bit difficult to feel something. That's the current limitation of the brain-machine interface. We can send signal from brain, but we cannot feel the reaction. So we decided to use the big toe to feel the reaction, reactive force. But yeah, but I believe it's possible to integrate our technology with brain or nerve system.
It also reminded me of the study of David Eagleman, if you have heard of him. His studies about brain. Well, he's trying to like create new senses through our bodies. Like whenever, let's say, the currency rate changes, he is trying to imply new signals to put some actuator here, and brain tries to like analyze that and tries to get the feeling of, oh, there's a new sensation here and I'm sensing that. That's probably what you're doing with your study, right?
Yes, but we have to be careful about the difference. If we use the vibration, we can be noticed something, but the vibration is different sensation of the stiffness or hardness. So by using the vibration, we can feel something, but that is totally different from the actual sensation. That's the important point.
Okay, I get it. Thank you so much. And
Thanks so much.
I have one more question, if it's
Yes,
okay.
please. Yeah.
About the fishing guy who is fishing from afar, do you think this also can be integrated with VR technology so that it can give you a real-time feeling of you're actually there with maybe fisheye camera and stuff, do you think?
Yeah, of course. And in the example of draw arm system, we use head mount display to see the visual information of the remote area.
Yes.
Yeah. That's very easy to use the head mount display.
And my last question, if it's okay.
Yes, of course.
I assume there is a huge cost coming up with this, and which industries do you think they are more into like implementing this technology in their usage? For instance, I'm not sure about that, but maybe the operators who are trying to grab the huge stuff may not be so interested in the stuff, but maybe at bomb disposal, like dangerous jobs, or maybe like in the problems in the nuclear plants, right? When there's a leakage, it can be also implemented in that area. So you're also working with companies, and which companies, what type of companies, which fields are more interested into your work?
Actually, we are joining with a lot of companies and various companies, but we think this technology can be used for military application, and we want to avoid that flow, or we don't want to use this technology for the military application. So from the military problem and the cost problem, this technology should be used in manufacturing processes, not the consumer applications. Yeah, VR is very popular in the consumer side, but that will be there is a cost problem. So I think industrial company or manufacturing company or heavy equipment company, that kind of company using high cost equipment are the best way or best application.
Okay. Thank you so much for your time, and I will leave my seat to other people because other people also have questions. But if nobody else has, I have more questions. Maybe
Okay,
later.
thank you for
Thank you so much.
wonderful question. Thank you so much.
Yes, thank you very much. So I think we have Ronald who has a question.
Yes. Thank you, Professor Takahiro, for your presentation. In fact, I was thinking about that. Okay, your system could complement very well with augmented reality applications, which I think normally you have talked already of the idea, like this Microsoft HoloLens Have you explored that idea? Because I was watching some videos where they are kind of do technical service from distance. You have the main operator in the base, you have the technicians in place, you give them feedback, do this, etc. Have you explored that idea, or is not in your research interest?
That's a little far from my expertise, but we have to be careful about the time delay of the visual information. How can I say, we have to synchronize the haptic feeling with the visual information or auditory information. From that viewpoint, of course, the reality or precision is very important factor for the visual devices. Uh, but also we need a low latency system.
So how bad can that problem be? Have you tested that? It's really so bad.
For example, in a visual system or TV, the processing time is about 33 Hertz, but the processing time of haptic technology is 1000 Hertz. So there's a huge differences, and the acceptable time delay of the haptic transmission is about 20 milliseconds. So there's a huge differences between the acceptable communication delay of the visual system and the acceptable communication delay for the haptic system. That's the very important point.
Or you're saying that it would basically confuse the user. If you have the vision and the haptic, it would be like, wait, I'm not feeling the same thing I'm seeing. Oh,
confusion. And also the operator will feel bad. So the delay will, how can I say, the feeling like driving a long time.
Yeah, like kind of playing a video game with low frame rates.
Yes. So I don't know the differences of that HoloLens or Oculus, but we have to pay attention to that kind of properties.
Okay, and probably just to finish, because I was seeing a lot of this application, because I saw this robot chef that you can teach them how to cook, and then it will cook in place. So I think you can also apply your research to that, right? Because you have to be very careful when cutting, etc.
Yes, and by storing a lot of data for like cutting, we can select which cutting data is suitable for this task. Then we can select the best data, and we can reproduce the best data. That's a concept.
Great. Thank you very much.
Thank you very much.
Thank you. Maybe some other questions?
Yeah, I have a question.
Yes, please. Yes, Mara.
That's okay. I was thinking, like, what are the more difficult aspects that you had to face? Like when grasping an object with the tactile sensors?
Yeah, there are many difficulties, but for now, the effect of inertia of the robotic system is the serious problem. I mean, if we want to generate high force, then the system will be big, and we will feel the inertial force of the system. That is a difficult, serious problem. And also communication delay. We have to solve the effect of the communication delay. And also we can record and reproduce the motion data, but the motion should be should adapt to the real object. So we have to think more about how the robotic system can adapt to the various objects.
Okay, thank you.
Thank you.
Okay, maybe we have some question. Yes, yes, please.
Oh, your mic is not.
Maybe yes, turn on your microphone.
Yeah, you're muted.
No, I think yes. Hi, Takahiro. My question is, you put the example when you were talking with Ronald. You can select the best set of operations when you are cutting for a certain object. You can select the exact force, which is the best. But is this applicable also to, for example, long distance surgery? Because in surgery, every patient is like very different from another one. I want to know how accurate is this kind of technology to long distance surgery? Is this really applicable? Thank you.
Okay. For that direction, we have to be careful to two direction. One is how we integrate the divided or partial data. For the long surgery, we have to select short motion data and integrate those short motion data into one for long surgery. So we have to think about how we integrate and how we can generate the long motion data. That's one point. And another one is how we can make the robot adapt to the various patient. But maybe the differences between the patients are just the stiffness or radius or a small differences of the places. So the variation is not so huge. So yeah, so those are the problem, but I think those are not the serious problems.
Okay, thanks. This was it.
Okay, thank you. Any other question? Okay.
Questions?
Yes, yes, Shiyu, please.
Yeah, thanks for your presentation. And I have a question related to the communication delays you are facing when you do the remote haptic task, like some researchers is trying to doing a drilling task in Singapore, and the real task is performed in Japan. And what kind of the communication delays you are facing with, and how you solve this problem?
Okay. How can I say? Time delay is highly depending on the quality of the communication. If we use online communication, and that's the fastest communication. But if we use how can I say Wi-Fi, then that causes some delay after the wired communication. And also in the drilling application, we used smartphone. I mean the tethering. So the time delay was much longer than the online communication. And the problem is just the pure time delay and also fluctuation of the time delay and packet loss. Those are the very serious problems for the teleoperation system. And the solutions so far are estimating the time delay and staging some data called as buffer for compensating the time delay. And the most simple way is using high quality communication line. Yeah, there are a lot of solutions, but these are the main solutions.
Okay, thanks for your answer.
Thank you so much.
Thank you. Maybe a last question. Okay. So thank you very much again, Professor Nozaki, for your presentation.